In this video, I want to discuss a little bit more detail the idea of a lower bound. So we've already seen kind of the general intuition before lower and upper bounds, right? And we've discussed upper bounds in depth. Kind of on the flip side is lower bounds, a function that's always less than another function. These are kind of nice to have, but they're actually hard to derive in practice. So we won't spend all that much time on them. So here in our picture, this time I'll label things a little bit differently. Let's say, right, that this blue is my f of n. And this red here is my g of n. Now, from the name, right, lower bound, you could say, okay, yeah, this red function, right, g of n, right, which is going to be my lower bound for f of n, is a function that will always be less than f of n. Okay, so it's kind of like a minimum cost, right? It'll always take me this number of operations to do something. So that's fine. Now, when we actually go to write these things, we're going to have special notation like we did for upper bounds. So when we have a lower bound, we'll use the omega symbol. So we'll say that basically f of n is omega of g of n, right? F of n is lower bounded by g of n. Just the kind of the standard syntax, standard nomenclature, right, is to call that omega, right? A lower bound. So here we have the definition, again, right, the mathematical definition, and it's basically just flipped from the definition we had for big O. So in this case, we'll say, right, well, here, right, is our kind of our first kind of overview syntax, right? Our f of n equal omega of g of n, right? That's how we say that f of n is lower bounded by g of n, right? We write it like that. But then, right, we have our definition, which says, okay, f of n, right, is omega of g of n, if and only if f of n is greater than some constant times g of n, right? For n greater than some x sub 0, where x sub 0 is a constant. So this is basically identical to the big O definition we talked about in the last video, except that this little equality symbol has been flipped, right? So instead of it being less than, it's now greater than. So now we're saying that f of n must always be greater than g of n. Pretty much all the logic that we talked about for big N will still hold here. So if I want to do something like figure out or prove a bound, right, I can follow the same algebraic steps. Now, if I want to write an omega, right, from a growth function, things are maybe a little bit tricky. Basically, you can go and say, oh, maybe I set n to 0, right, figure out what exactly is the constant that's left over, and that would be my function. So it would be relatively easy to do. Now, the problem is that in general, lower bounds aren't too useful for us because a lot of times they end up being the ones we can write, just some constant value. And it's really not all that useful to know that, oh, hey, I'm going to always have to do 10 operations. That's not always useful, at least for a specific algorithm. Where omegas really are useful is a special case kind of where we can write a lower bound for a problem itself. So something like searching, right? And we already had a discussion in a previous section about this idea of, oh, there's different ways to solve that one problem. What is the fastest way I could possibly do that? Well, one thing people actually do is say, okay, for that problem, so for example, searching, try to find the omega of that, right? What is the lower bound for it? What is the least amount of work any algorithm could possibly do for this particular problem? So for like searching, the lower bound is going to look something like omega of log n, right? You need to do at least that much work to find out if an element is in a collection. So that's kind of useful, right? If we can characterize or try to understand a problem itself. Now, in terms of an algorithm, it's not always useful because it's just saying, oh, hey, there's going to take at least this much time. Really, upper bound is more useful because then we have a guarantee, right, that this program will never take more than this amount of time. So in general, just keep in mind the omega symbol. We'll use it a couple of times, but not too much.